Alright, so after reading your feedbacks, I decided to make some changes to my tutorial. I know a lot of you want me to do other questions instead of the tutorial activities, but unfortunately I cannot do that because all the other TAs are doing the same thing. So I should do the same thing as well. But I don't want to be the TA who doesn't listen to people's suggestion. So instead of spending all my time doing tutorial activities, I will make some adjustments. For example, this week, since you guys have the quiz in 2 days, so I will do part of the tutorial activities. The reason is because only the first two activities, so only the first 2 points, if you look at the learning objectives, only the first 2 points are related to your quiz. The third one, and the fourth one are for the next chapter. So what I plan to do is we'll do 1 and 2, and I will use the rest of the time to do a short quiz review. And if we have more time, which we don't, because based on my last tutorial, we don't. So we don't have enough time, so I will record the other 2 activities and upload them on YouTube, so you can have a look at those as well. Okay, so that's my plan. Any question for now? Okay, seems like you guys don't have any questions. So I want to talk about some common mistakes from your problem set. So the first one is from 2.5.1. You need to show S equals to T. Okay, as we mentioned many times before, if you want to show 2 sets are equal, you have to show they are subsets of each other. Some of you only showed one direction, which is not complete. Okay, so please, when you want to show 2 sets are equal, you have to show they are subsets of each other. That's the first common mistake. The second common mistake is from 2.5.9, part C. Part C asks you, is the natural number an element of real number? Okay? No, it's not true. Natural number is a subset of real number, but it's not an element of real number. Why? Let me give you an example. So suppose we have 2 sets. We have A equals to 1, 2. B equals to 1, 2, 3. Now, can you say A is an element of B? Yes or no? No, okay, this is not true. No. A is a subset of B, but A is not an element of B. The elements of B are 1, 2, and 3. Okay, so this is not true. For the same reason, this is not true. Okay, natural number is like a set of 1, 2, 3, 4, and continue go on. And real number has a lot of numbers, has 1, 2, 3, 4 as well, has like 0, let's say square root of 2, 1, 0.0001, something like that. So it's a collection of numbers as well. It does not have the set of natural numbers in there, so it's not an element. A third common mistake comes from, what's the third one? Oh, question 1. They ask you how many subsets does the set of empty set have? Okay, so before I do that, let me ask you, is this the same as empty set? No, okay, no. The empty set and the set of empty set, they are not the same thing. This, it's called the empty set, which means has no element in there. It's empty. Okay, but this one, it has one element, which is the empty set. So the empty set is an element of the set of the empty set, but at the same time, the empty set is a subset of the set of the empty set. Okay, because, well, it has nothing in there, so it's a subset of this. Another subset of this is the set of itself. So this one has two subsets, okay? Not just one, it has two subsets. Another common mistake from the same question is this one. The set of the set 1, 2, 3. How many elements does this set have? One, okay? Has one element. The set 1, 2, 3 is the element of the set. Of the set 1, 2, 3. And the subsets would be the empty set and itself are the subsets of the set. Okay, so those are the common mistakes. Please make sure this whole thing, this whole thing is your element, okay? Not just the single elements in there. Another question that I want to ask is how many subset does the empty set have? One, okay? Has one subset. Which one is it? Anyone know? Itself, exactly. Okay? That's the only subset it has. Alright, so those are the common mistakes. Let's move on to the tutorial activity. So, learning objectives, by the end of the tutorial, you guys should be able to do the first two because we don't have time to cover the last two. So you should be able to prove the value of a given expression in the field of 3 or 4 elements. You should be able to prove the negatives or reciprocals are unique in the field. 3 and 4, I will record video and upload on YouTube. So, field axioms. Last week, someone asked me to review this, but I didn't. But after reading your feedbacks, I feel like a lot of you want me to review the certain concepts, so go over this quickly. Now, can someone tell me what's the definition of a field? So we have a set F with operations. How many operations do we have? So we have 2 operations. One is addition and one is multiplication. And we have 2 special and 2 special distinguished elements, 0 and 1. Zero and 1 is a field if for all x, y, and z, in the field we have the following axioms. Before we move on, I want to emphasize something. Okay, before we talk about the axioms, I want to emphasize something. First of all, the two operations, addition and multiplication, they might not be the usual addition and multiplication you know. Okay, after you went to the lectures, you should have seen that they might not be the usual operations you know. Second, the two elements 0 and 1, they might not just be the number 0 and 1. They just mean the additive identity and the multiplicative identity. So they might be something else. They might not be the number 0 and 1, but we just want to make sure we have the additive identity and the multiplicative identity. Well, you might never see the case they are not the number 0 and 1 in 102, but that's true. So anyone can tell me one of the axiom? Guys, you should know the axioms by heart. They're really important. Closure, okay? Closure. That means x plus y is in f and x times y is in f as well. So it's closed under addition and multiplication. Number 2. Anyone else? We have associativity, TVT, which means that you can add x, y first, or you can add y, z first. Add your bracket. Or you can multiply x, y first, or you can multiply y, z first. The third one is pretty similar, yeah. Commutativity, okay, so commutativity, which means you can x plus y equals to y plus x, and x times y equals to y times x. And the fourth one, someone said reciprocal. We'll talk about that later. Let's do the ones that are similar. So we have distributivity, which means you can have x times y plus z. You can distribute it outside. That can give you x times y plus x times z. Now I want to talk about those two elements. Okay, so we have identities. The first one, we have additive identity, which means 0, which is our additive identity, plus x equals to x for all x in f. So 0 is called the additive identity of f. And we have multiplicative identity, which is 1. So 1 times x equals to x. And our 1 is called the multiplicative identity. Identity of f. Lastly, let's talk about inverses. So as some of you mentioned reciprocal, we have reciprocal and negative. So number 6, inverses. Please know all the axioms by heart, okay? Really, really, really important. For any x in f in a field, there exists another element w in the field such that x plus w equals to 0. And in this case, your w is called additive inverse or in other words, we can call it negative. Okay? We usually denote W notation. We usually denote it by W as minus X. But remember, this is just a symbol. It doesn't really mean minus X. It means that it's the additive inverse of X. It's a negative of X. The second one is multiplicative inverse, which is also called reciprocal. So for any, here is a really important thing. For any non-zero, it has to be non-zero, okay? For any non-zero X in F, there exists W in F such that X times W equals to 1. And in this case, your W is called reciprocal or multiplicative inverse. Again, you can denote it by X inverse. Again, this is just a symbol. It doesn't really mean 1 over X or something. It's just a notation, okay? It's just a notation. Any questions so far? Question? This should be clear because I'm pretty sure it was covered in lecture. Please make sure you remember everything. Please make sure you remember their name because, okay, those names, make sure you remember those. Additive identity, multiplicative identity, negative, and reciprocal. Because when you do field questions, whenever you use them, you have to write down you used them, okay? You have to refer to the axioms you used. For example, let's look at activity 1. We have a field with 3 elements, 0, 1, and x. They want you to show that 1 plus 1 equals to x. Okay, I will give you 5 minutes to work on this. While you guys work on this, I'll write down my solution to save time. And after I finish writing, we'll take it up. So copy down the question and work on it. Don't look at the screen because I'll write down my solution. Okay. All right, let's take it up. So to do this question, I want to use a method. It's called elimination. Let me write it down for you. Elimination. Okay, so this is the method we're using. Since we know f has those three elements, we know f has those three elements, we want to prove 1 plus 1 equals to x. So if we can eliminate 1 plus 1 equals to 0 and 1 plus 1 equals to 1, then 1 plus 1 has to be equal to x because this is a field, and by closure it has to be the last one left. So that's the idea. As you can see, first of all, I proved 1 plus x equal to 0. This might seem unrelated, but the reason I do this is because of this. So when I prove 1 plus 1 equals to 0, let's say we don't prove this. We do it directly. Let me use another color. So if we have 1 plus 1 equal to 0, and I want to do it directly, so I want to add minus 1 on both sides. Okay, and then this will give me 0, so 0 plus 1. This is too bright. Probably you guys can see it. Oops. Let me use another color. Oh, which color is better? This is better. Okay, so that's gonna give you -1, and that's gonna give you 1 equals to -1. So if you reach this is not a contradiction. Okay, some of you might think this is a contradiction, but it's not a contradiction. The reason is that this means that 1 is the additive inverse of itself. That's totally fine. That's not a contradiction. So you cannot reach any contradiction here. Okay? One thing I want to emphasize is that this, okay, -1 here, it's not the number -1. This means the additive inverse of 1. It's not the number -1. We don't have that number in the field, but we do have the additive inverse of 1 in the field. Okay, so we used this. Okay, we use this axiom. We know since 1 is in the field, we know that it's negative, it's in the field as well. So this doesn't mean the number -1. This only means the additive inverse. So if you don't prove this, just by doing this, you don't reach any contradiction. We have no contradiction here. That is why I need to prove this. Why do I pick this? Why do I pick 1 plus x? The reason is that I want to write 1 plus 1 equals to 1 plus something. Okay? I want to write 1 plus 1 equals to 1 plus something so that I can add -1 on both sides to eliminate my 1 so I can get 1 equals to something. So what's my something? If you remember, I remember that 1 plus x equals to 0. If you don't, that's okay, because, well, you only have 3 elements. You know 1 plus 1 is not 0. You know 1 plus 0 is definitely not 0, because 1 plus 0 equals to 1. So the rest, it has to be 1 plus x. So let's prove 1 plus x equal to 0. We use the same method, elimination. We eliminate the case of 1 plus x equal to 1 and 1 plus x equals to x. Okay, so I will explain one of this because the rest of all are all the same. Okay, so we have 1 plus x equals to 1. You want to get rid of 1 on both sides, so you add its additive inverse, which is -1 here, on both sides. That's going to give you 0. That's going to give you 0 as well. So eventually we can get x equals to 0, which is impossible because we have 3 elements f 0, 1, x. They are distinct elements, so they cannot equal to each other. So that's impossible. We know 1 plus x cannot be 1. And you do the same thing, you can show that 1 plus x cannot be x. That's why it has to be 0 by closure. One thing I want to emphasize is that when you add something on both sides of the equation, for example, this one, okay, I added -1 on both sides. When you add something, you either add it to the left-hand side on both, or you add it on the right-hand side on both, okay? You cannot do like one here and one here. You either add it to the left-hand side on both or right-hand side on both. Also, you cannot add to the middle, so you cannot add right in the middle between 1 and x. Okay, that's one thing. The second thing, whenever you use an axiom, please write it down you used it. Okay, really, really important. It seems really long, but that's what field questions look like. Okay, please make sure you write down the axioms you used, and when you add something, you add it on the same sides. Other than that, there's nothing I need to talk about. Any questions so far? Do we have to write one using verses? Yes, you have to. Okay, any other question? So whenever you use, I got the left hand side, what is the working you did on the right? Which left and which right? The right side of the page. So this page, this side. Oh, so we want to eliminate 1 plus 1 equal to 0 and 1 plus 1 equals to 1. So this side, I'm eliminating those two, because you want to show 1 plus 1 equal to x. So this side of the work, okay, this side is just for you to prove this is not true. It's like a supporting thing so that you can prove this is not true. Okay, but this is a key steps. Any other question? So I did all those work just to show that 1 plus 1 cannot be 0. Any other question? Okay, if no question, let's move on then. Activity 2, for this question, I'm not gonna do it because I did it already. I will tell you where exactly I did it. So there is a video. It's called something something field part 1. Okay, you can find that on my Quarkus page. Check part 1, it's around 9 minutes and 10 seconds. I did this question, okay? So check that. I want to save more time for other questions, so we're not gonna do it. Activity 2, part B. This was a quiz question from last year. Okay, so please make sure you know how to do it. Again, I'll give you 5 minutes to work on this. While you work on this, I will write down my solution. And then after I finish writing, we can take it up. 5 minutes, guys, 5 minutes. Are we allowed to create? No, you cannot. You cannot. You are only allowed to use what's given, which is the axioms. Okay, you cannot use any table. You cannot use any chart. You use that, you get 0. You can only use the axioms. Well, in this case, you can use this as well. Wait, did I even do this in my last tutorial? I don't think I did this in my last tutorial. But we have 15 minutes. We have more time than last tutorial, so I'll do it. Wait, it's 0. Okay, so this is a proof. It's pretty similar to the last activity. Instead, we have 4 elements here. So we want to show a squared equals to b, and you can use ab equals to 1. Okay, so we want to eliminate a squared equals to 0, 1, and 8. So if it cannot be any of those, by closure it has to be b. So let's let a squared equals to 0. Since a is non-zero, remember, if an element is non-zero, then the inverse exists, right? So since a is non-zero, a inverse exists. Let's write it down actually. Since a is non-zero, a inverse exists. Okay, so since we have a inverse, you can multiply a inverse on both sides. This side will give you a times a, 1 times a, and this side will give you 0 by reciprocal and claim. So I used reciprocal on this side and I used the claim on this side. The claim 2.3.2 is talking about if you have any element in the field, then 0 times any of the element x equals to 0. So I used both, so I need to say that I used both. Anyway, and this will give you 1 times a equals to a, so a equal to 0, which is not possible because our f has 4 elements and they have to be distinct, so they cannot be equal to each other. And for the second one, I let a squared equals to 1. I know ab equals to 1, so a squared equals to ab. Again, you multiply a inverse on both sides and you'll get a equals to b, which is impossible as well. And you do the same thing for a. Let a squared equals to a, multiply a inverse on both sides. I'm missing one here. It's associative. So I multiply a inverse on both sides. I added bracket, that's why it's associative. And this will give you 1 times a, which is a equals to 1. That's impossible as well. So we eliminate all 3 cases. That means a squared can only be b by closure axioms. Any question? Question. How do we prove without eliminating? For this type of question, the best way is using elimination. I don't think you have a direct proof, to be honest. I can't think of any direct proof for now. I will think about it. If I come up with a proof, I will tell you. Oh, in that case, it's different. I can't give you an example here because in 102 they never teach you that. But check. Okay, I will answer I will answer a question later. For Andre, there is a example. Let me show you. Okay, I posted on my Quarkus page as well. So field, where is field? Oh, here. So in this tutorial, I covered question 4 here. Okay, and it's infinite field. It's not a finite field anymore. Okay, so question 4 here. It's not really what we were doing here, but in this case, it's a good question. So try that. For length, let me answer your question. How do we know if we need to prove something else before we work on the main proof? You work on the main proof first, and if you get stuck on somewhere, that's when you realize you need to prove something else. Okay, does that make sense? So for example, our last proof, here, you should work on this first. Just like here, I work on this first. I realized this doesn't give you contradiction. That's when I realized, oh, I need to prove this first. Okay. All right. So I want to do some quiz review, but we only have 5 minutes left. So I'll quickly talk about this. So for a quiz, you have 3 parts. The first part, sets, which we did a lot of examples already. Sketch the sets in R2, we did that. Hopefully everyone knows how to do that. So check the tutorial. I don't remember which tutorial, but it's one of the tutorial. Normal set identity, we did a lot of questions on that too. So check tutorial. You have tutorial, you have problem set, B, C, D. They all gave you normal set identity. What you didn't do is this one. Set identity involves Cartesian product. You didn't do that, so we'll do that today. Okay, so I'll use the last today. We'll use the last few minutes to work on one question that looks like this. Set identity involves function. This is in one of the video. Please check that video. How do you know which video to check? Quarkus page, okay? Go to Quarkus page. Go to here. So let me show you. So this here. Set question involves function. Check this video and you should be able to do those type of questions. Alright, so we don't have time to do that. Function, we did a lot. We did a lot of function proving tutorial. We proved image in tutorial, so we did a lot of those. Not gonna do it again, but I do have a question here again. Fields, we did a lot as well. So for function and fields, I have videos as well. Okay, so for image, here is a video. Check this. Image proof. If you don't understand anything, check that. Check last week's tutorial recording. So if you don't understand this part, check those 2 videos. For fields, if you don't understand the concept, you need to review this again. Check those 3 videos. Okay, those 3. Field part 1, part 2, part 3. If you understand it, don't waste your time. Do more questions. If you don't understand, you need any clarification, check those videos. But yeah, so our last thing is that I want to do this question. So sets, I want you to try this question. Okay guys, try this question. Again, I'll write on the solution while you guys work on this, but please try it yourself, okay? This was a quiz question as well, so you should be able to do it. I was a TA when the question was on the quiz as well. Students did not do well on this question. They did horrible on this question. So please make sure you know how to do it, okay? I want to reconnect it. Okay. Ah, there is a typo. I thought I fixed it, but it seems like I didn't fix it. It's union here, guys. Sorry. I guess I used the old version. Is there anything needed besides that showing into? Wait, which one are you talking about? Andrew, what are you talking about? Is it important for the proof? A intercept B minus B intercept C extra. Oh, you mean question 1? You mean this question? Oh, this, I mean, it's pretty important. It's pretty important. It's one of the quiz questions as well. So all 3 questions were quiz questions. So is it important for 2? No, it's not. 2 and 1, they are different questions. They are not related to each other. They're just like 3 separate set questions. All 3 questions were from quizzes, so make sure you know how to do them, okay? Let me just finish writing this. Oops. For the question 9.3, Cartesian product. Okay, so since I finished writing, let's talk about it. Wait, how come we can group out x and y separately? I'll talk about it, okay? I'll talk about it. After I finish explaining, then you ask questions. Otherwise, it's gonna take too much time. So, this is just like the other question. You prove one set is a subset of another set. So you pick arbitrary element from this set. But since we have Cartesian product, you know that the elements in the set looks like this, x, y. So we'll pick an arbitrary element which is xy from the set. That's going to give us xy is in a Cartesian product C, or because it's union, or xy is in B Cartesian product D. Okay? Since we know this, so recall the definition of Cartesian product, you should know that this means that x is an element of A and y is an element of C. By the definition of Cartesian product, if you don't know what I'm talking about, you have to review that part. It's really important, okay? And same thing, because of this, we have Cartesian product B, Cartesian product D. So that means x is from B and y is from D. That's why we have this line. Now, we know that x is in A or x is in B, and we know that y is in C or y is in D. That means x is in A union B and y is in C union D. And you use Cartesian product again, you can put them together. That means xy is in A union B, Cartesian product C union D. Okay, so that's how we show this is a subset of that. So that's the end of the proof. Any question now? Right side. No. You just need to prove this is a subset of this, because they ask you to prove this, okay? So this is where I want to emphasize. Why is it or? Because it's you. Where is it? Because here, it's union. That's why it's or. You don't understand the logical. Review the definition. Cartesian product, review the definition. So basically, Cartesian product means this. So if we have xy in A Cartesian product B, that just means A is an element of X is an element of A and Y is an element of B. Remember last week or the week before when we draw a Cartesian product A? So for example, this is A, this is B. Let's say A is 0, 1 and B is something like 2, 3, 0, 0, 2. Okay, so 0, 1, 1, 0, 2. So that's gonna be something like this. Okay, so that's Cartesian product. So all the dots in this rectangle, that's your A Cartesian product B. So those are like pairs, like those are like points on the plane. So remember, if you have this, then your X is in A, Y is in B. Okay, if no question, here's what I'm gonna do. This is the end of the tutorial. You should try the rest of the question, okay? You can find the file on Quarkus. So let me show you again. Go to module, you go to tutorial material, go to tutorial 9101, 9106 will be in, and then you can find week 4 tutorial 4. So you can find the slides here. Work on the other questions. Let me see if I fixed it. Well, I didn't fix it, so I'll fix it later, okay? So here's the typo here. Typo here. I'll fix it later and upload a new one. Here, typo. I thought I fixed it, but whatever. So find this, do the other questions, except especially the fill question and set question, and this question as well. And later, probably tomorrow night, I will upload videos explaining the rest of the question, including tutorial activity 3 and 4. But before you watch the video, please try the questions yourself. If you need more practice, there are a lot of practice because a lot of people were like, can you post more questions with solutions? I did already. It's here. Everything is here, okay? So you check other resources. I post the tutorials worksheets here. Try those questions. I will post the solution later as well, okay? So try all those questions. Sets. So sets, I have a lot of questions. So tutorial 2, try all of those. And the solutions will be posted as well, so you can check your solution as well. And if you and also do your problem set D, okay? So because it's gonna be based on that. And there's nothing else I want to say. Is there any question? If no, you can leave. Guys, you can leave. If I passed time already, you can leave. If no, you can leave. It's the end of the tutorial. All right, good luck on your quiz, and yeah, that's all I can say. Good luck and do more questions. Make sure you understand all the concepts, okay? If not, check the videos. Is it normal to take 2? No, it's not normal. If it's gonna take you 2 hours to solve one question, that's a big problem because you only have 1 hour to solve 3 questions for the quiz. It's not marked. It's for practice. For practice to prepare your quiz too. Alright. Again, as I mentioned before, average, I don't know. It actually depends on the TA because I realize every single TA has different standard. So yeah. Okay, again, I didn't want to say this, but when you do practice, please make sure you can finish each question within 10 minutes. Okay? If it takes you longer than 10 minutes, then you don't have enough time to finish the quiz. You need to write the final proof. But, okay, make sure you justify your steps. For example, especially for failed question, please, please, please make sure you write down whatever field axiom you used. Okay? This is really important. Make sure you justify your steps. You only need the final proof, but your final proof should include the justification. Why did you do that? Okay? Any other question? Okay, okay, that's it. I'm gonna stop recording. How do you eventually get faster? Yeah, you do, you do. You get much faster as you solve more problems. If you are trying to remember, then you cannot do well on this course. You have to understand, okay? So what I showed you, everything in blue, if you're writing this as, if this is your quiz question, you should have everything here. If you're missing something, you don't get full mark. Okay, you should have everything here. And for set question as well, so you don't skip any step. Like here, I use the definition, then I write I use the definition. Okay. You don't know how to understand though. Let's just go over each proof. You don't move on until you understand everything. Okay. It's like writing an essay for each proof. No, don't write essays, please. Don't write essays. I didn't write any essay. Okay, please keep your proof short and concise. Don't write essays. I didn't write any of the essay. Okay, you write what's necessary and you don't skip steps. Please don't write essays because I'm grading quiz too. I don't want to read essays. All right, you can leave now. I'm gonna stop recording and good luck, everyone. You're welcome. Bye.